All right, so back to the Kalman filter. I know it's been quite a while since we talked about this, so I'll briefly review what we covered last time, but not at great length. So we're in the world of linear systems for a little while, and I know some of you were asking at the last time I was talking about this, please add an example with card tracking for the Kalman filter, but you can't. Card tracking is nonlinear, Kalman filter is linear. We can do it with the unscented Kalman filter, so I'll do it then, but we can't do it with a Kalman filter because it's nonlinear. So here are the here's the linear state space model and the notation I'll be using for this set of slides. And again, I'm trying to follow the book pretty closely, but my notation still differs from the book a little bit. So we've got our state vector, and Goldberg's, by the way, it's really nice to see a state space model with such a high-dimensional state space, the vector being in such a high-dimensional space. 16 elements, that's more than I think we've seen so far. That's kind of neat. Anyways, here's the state vector, and it's a linear combination of what the state is at time in by some known but possibly time-varying state transition matrix. And then we've got our process noise that's additive, and then we've got our measurement model that's also linear, so you've got a vector of measurements that is some linear transformation, h of n, where that measurement matrix is known, times the state at time in plus your measurement noise. Standing assumption is that the process noise and the measurement noise are white. That basically just means that there's uncorrelated over time, and that they have known covariance matrices. Those covariance matrices can change over time. So you've got Q of n and R of n, and we'll see more on this later, but often when you're designing models, and earlier Andy asked, what's your prior knowledge? I think on Golriz's homework presentation, and I think the answer is our prior knowledge is that these coefficients change slowly over time. So you model it as maybe a random walk process with maybe a high initial state covariance because you don't know what they are initially, and maybe a relatively small process noise. But that process noise then becomes one of the parameters that you tune often with these algorithms. So often Q of n, it's often a diagonal matrix. People are often using a random walk model when they're talking about parameters that are slowly varying over time. But then you as an engineer have to decide what are reasonable values for those parameters. So this process noise is often one of the knobs you get to turn, the different elements of that for the different state vectors. And what you set those at is what will affect the performance. You'll see an example of that a bit later when we get through the Kalman filter. Then we've got our measurement noise. This is usually a function of the instrumentation and usually something you can characterize based on how well your measurements work. If you're getting GPS measurements, then you can take your GPS out and leave it stationary and measure it, where your state is not changing, the position isn't changing. So all of the variation in your measurements then is due to your measurement noise, and you get an idea then of what a reasonable estimate is for your measurement covariance. Again, this is just showing that it's white, so our covariance matrix is multiplied by this Kronecker delta function. So that just means that if you look at the noise at two different times, they're uncorrelated. It's only when they're the same that you get that covariance matrix. Same thing for the measurement noise. And in this development of the Kalman filter, I'm assuming that the measurement noise and the process noise are uncorrelated. But again, there are formulations of the Kalman filter recursions that don't require that assumption. That's just what I'm showing you because it's easier to learn the first time you're through this. But I wanted to mention that there are ways around that are more general. So,
sorry, previous, are we saying that R and Q are functions of time?
They could be, but they don't have to be. If you've got an instrument, like if you've got GPS or a measure of velocity, or you're measuring a respiratory signal, in those cases, usually it's reasonable to assume that your measurement noise is constant over time. There's nothing about your instrument that's changing. On the other hand, if you're working with physiologic signals and you're trying to lump in movement artifact as well, whenever someone is instrumented with sensors measuring their cardiorespiratory state, whenever they move, it causes these large amplitude artifact in those signals. And if you wanted to include that in this noise, then it may make sense during those times to say, oh, whoa, I've got far more noise variance during this time than I do normally. So there are some applications where it makes sense to think about modulating that noise or having it change over time. You have to be careful on how you do that, because the assumption is that you know what the noise variance is, and it's not something that you're trying to estimate. If you're estimating it from the state, then you have to be careful about how you do that. But yes, it can be time varying, but it doesn't have to be, and usually it isn't. But there are some applications where it makes sense. So as always, we're trying to estimate the state, and we've got knowledge of the dynamics, and we've got noisy measurements that somehow linearly relate to the state. And we're going to estimate the posterior mean. That's what the Kalman filter gives us, so we can't do medians or modes. We're going to try to estimate the mean of the posterior. And this is most appropriate, of course, not only when you've got a linear system, but when your marginal posterior distribution is unimodal. If it's unimodal, then this will generally work well. You might say, well, wait a minute, it's a linear system. How could it not be unimodal? But one of the things I haven't said yet is what the distribution is of these noise terms. If those noise terms happen to be multimodal, then it's possible that your posterior would be multimodal as well. So that would be quite unusual. Most instruments don't work that way, and I've never seen a process model where the noise term is multimodal, but it's at least possible. So I have to state that, in the case where marginal is unimodal. And we're going to estimate X of n as a linear combination of all the observations, so of all of these measurements, up to either time in, or I should say up to both time in and time in minus 1. So I'll say more about that in a minute. So the noise is white. It doesn't have to be Gaussian to use the Kalman filter. It's a common misconception that you're limited to Gaussian noise. Still works well even if you don't have Gaussian noise. We'll be estimating the mean and the covariance as well, the state error covariance, so we can use that to get approximate confidence intervals and an estimate of the standard deviation of our estimation error. And we're going to assume that those two things are sufficient for tracking our posterior. People, when they're using the Kalman filter, never create the kind of images that we've seen earlier in this class where they're looking at the posterior, because there's no reason to. You've really just got an estimate of the state and then an estimate of how much uncertainty you have about the state. So it really comes down to two numbers for each element of your state vector over time. So, creating an image, you could say, well, I'm going to assume the posterior is Gaussian and then create that kind of image, but people normally don't do it because you've just got the mean and the covariance or the standard deviation of the state estimates. Okay, and then again, notational differences with a book. I am following the book very closely in going through this derivation, but I've got a different notation for the covariances, where I'll use this kind of norm notation for a matrix. This essentially means the expected value of the outer product of those two matrices. And again, there's the so-called filtered estimate of the state and the predicted estimate of the state. The filtered estimate is given all the measurements up to and including the current measurement at time in, and the predicted is everything except for the most current measurement at time in. So the Kalman filter just works with both of these, and so they're needed frequently. The book and a lot of the other books and other references will use the superscript plus and minus, but I prefer this notation where you've got a vertical bar that is a symbol for indicating what measurements you have from time 0 up to whatever time is indicated there. And the letter to the left of that bar is the time of the estimate. So we're estimating the state at time in, given all the measurements from 0 up to time in minus 1. And I think this is where we left off last time. So we'll have, again, this, what I'll usually call the filtered estimate. Sometimes it's called the a posteriori estimate. And I gotta figure out how to turn this off. And then we also have the predicted estimate, or what is sometimes called the a priori estimate. The posteriori and priori are referring to whether you have the measurement at time in or not, whether you're including that or not in your estimate. And you would expect that your filtered estimate will always be better than your predicted estimate. It should be, because the Kalman filter is optimal, and including another measurement should only ever help things. If there's no information in that new measurement, then you should discard it, right? It shouldn't make things any worse. So you would normally expect your filtered estimate to always be better than your predicted estimate. And as always, we have to start off with an initial estimate, and this has to be something else that you know, something that's given. So you've got to have an idea of what your initial state vector is. And the application goal res mentioned is kind of neat, because you might say, well, look, I know that the average resting heart rate of maybe an adult is, 70 beats per minute? So you might have an initial idea of what that heart rate is, but you might say, but there's a lot of variation from people depending on what kind of shape they're in, how old they are, a variety of things. So you might say, my initial estimate is going to be 70 beats per minute, but with covariance that is based on a standard deviation of maybe 20 beats per minute, for example. That might be reasonable for that part of the state vector. In other cases, if you're estimating the coefficient of one of those harmonics or one of those sinusoids, you might be like, I have no idea. It's not going to be bigger. If you're measuring a pressure signal, you know the pressure signal isn't going to be larger than maybe 180 millimeters of mercury. So you might say, well, I have no idea what it's going to be, but it will be positive, and it will be no larger than 180. So I'm going to say 90 with a standard deviation of another 90. That might be reasonable for that, for example.
For some of those, too, it can be any distribution you want. It just has to be white for the process. So you could do it as uniform or something.
But with a Kalman filter, we're really only specifying our initial estimate, and the uncertainty is expressed only as a covariance. Usually that's diagonal, and the covariance can easily be calculated from the estimated standard deviations. So in that case, you're just specifying a mean and a standard deviation, not an entire distribution. If you have the entire distribution, you would just calculate those two parameters for it if you were using the Kalman filter. So that's one thing that's different than a particle filter. With a particle filter, you use any distribution you want. You know, say, well, I know it's no larger than this or smaller than this, but it could be anywhere in that range, then you'd use a uniform distribution. With a Kalman filter, you don't have that flexibility. You've just got the mean and the covariance. So those are things you have to provide. But again, if you don't know, then you usually assume a value. Maybe it's 0, depending on your application, with a very large variance. But don't make it insanely large. Or you may run into numerical issues. Use something that's reasonable for whatever your application is. But you got to start off with that. So you provide these two things. And then the other thing the Kalman filter keeps track of is the state error covariance. And a lot of people get confused about what this is. There's two of them. There's one for the predicted, and there's one for the filtered. And I'll denote those as P of n given n minus 1 or P of n given n. And again, this is really just, what are you looking at the covariance of? We're looking at the covariance of the difference between what the state really is and what your estimate is. So it's the error covariance. This is an error because you've got the true minus your estimate. That's the error. So this is the state error covariance. A lot of the references when they're describing the Kalman filter will talk about this just being a covariance matrix without saying what it is the covariance of. And a lot of students and people, when they're first learning about this, will think it's the covariance of the state, which it isn't. Or they'll think it's the covariance of the estimate, which it is also not. It's the covariance of the error. So it's that difference. And that is the same as the variance of our marginal posterior. So for those of you that had a linear state space model and then used a particle filter, used a sledgehammer to hit a thumbtack, when you look at your posterior and you see, oh, it looks like Gaussian, it should be Gaussian. And if you were to plot a Gaussian generated by the Kalman filter, where you got the covariance or elements out of this matrix, then you should see basically the same thing if you have enough particles.
So in the second statement in this is not section, the bar, so x hat bar, the bar does that represents the ensemble mean, right?
Yeah, correct.
So shouldn't that be the same as the actual state if it's optimal tracking?
You might be right. I have to think about that, but I think you're right. I think you're probably right about that. Yeah, that's an excellent point. Yeah, I think let me think about that, but I think that's probably true. That's a great question.
What was it? Sorry.
So his question was, well, isn't this actually that? And you know, my only hesitation in that is that if this is the expected value of that, then that's not a random variable, whereas this is. So this would be, that's part of why I need to think about that. You have to think carefully about what these are the expectations over, because we've got all of our measurements and all the noise that generated them, and those may be some of the differences. Go away, stop that. So I have to think about that. I'm not sure. Great question. Thanks. That'll be on YouTube forever. So the Kalman filter recursions conceptually, there's often a diagram when people are first learning about this to help understand how the algorithm works. And the way our book introduces it is a little bit weird, because usually I think of the first measurement as coming at time 0, but the book treats it as though there's no measurement at time 0, and so that's what I've laid out on the slide. So we start off with our initial estimate of the state and the initial state error covariance, and these have to be provided by you as the engineer designing the algorithm. This is what represents what your uncertainty is at time 0 before you have any measurements. We then make a prediction of what the state is going to be at time 1. So we still have no measurements because there was no measurement really at time 0. So we make a prediction from this initial state to what the state is at time 1, and then we calculate what the predicted state covariance matrix is at that time. And then we take into account the measurement that we actually got at time 1. And we update our predicted estimate and calculate what our filtered estimate is.
Functionally, is that some way to taking, because when you do particle filters, you essentially end up with the likelihood after that first measurement, because you haven't had any actual process. So does this end up working the same, or because it looks like you're actually stepping through your process model there, which you don't do necessarily for your first step with the particle filters.
With the particle filters, we start off with an initial scatter of particles, and that's equivalent to this step. And then with particle filters, the way I introduced it, we did get a measurement. That was the next thing that happened. And so that measurement enabled us to get this. So really, I think I started off with basically x of 0 given -1. So this is a little bit different in terms of how it's initialized. But in terms of going back and forth, whenever we took into account the likelihood and calculated the weights, resampled if need be, we would advance the particles forward in time and let them kind of scatter forward by applying the process model. So that's equivalent to this step. And then we would calculate the weights by taking account of the likelihood. So that would be equivalent to doing that step. So there is an analogy there. But the way the book frames this, the initialization of the particle filters, or of the Kalman filter, is just a little bit different. But the book's unusual in that regard. But I decided to follow it. But there is this back and forth between doing a prediction step and then taking account of your measurements. Yeah. So one thing to keep in mind that is a little bit different, rather than keeping track of weights, with a Kalman filter, we're keeping track of the state error covariance matrix. So we're always having to compute that as well. We're not just following the state, but we're also following that matrix. And so there's really kind of 4 things we have to do. We have to be able to, let me start here. We have to make a prediction of our state estimate. We need to be able to update our covariance matrix. Then we need to be able to take into account that measurement and get our filtered estimate. And we have to be able to update our predicted state error covariance into the filtered state error covariance. So there's 4 things we essentially need to do. after this initialization. But we're really going back and forth between predict, update, repeat, predict, update, and then I guess it's really predict, update. I shouldn't say repeat as the third step, because that's weird, isn't it? I'll update my slides. So let's talk about that first step of doing what's called the time update, or where you're really trying to do a prediction. So let's say we've got a great estimate that we're really happy of our state. Given all the measurements up to time n-1, we've got a great estimate of what the state is at time n-1. So we're starting off with that, and now we want to get a predicted estimate. Because we're working with the means, a lot of the derivation of the Kalman filter is driven by taking these expectations. And initially, when I show you these equations, I used a subscript here to indicate what you had measurements up until. So this is taking the expectation over all those noise terms and the initial state uncertainty, the initial state covariance, up to time n-1. But later I drop that just because the notation gets too cumbersome, and I'll just use the expected value. So we know that our state at time n is related to the state at time n-1 by the process model. And we know that our estimate should be the expected value of the state at time n given all the measurements up to time n-1. And if we substitute this equation in for x of n, then we end up with expected value of a matrix that's known times the state at time n-1 plus the noise. But the expected value of a constant times a random variable is just that constant times the expected value of that random variable. This expectation, another way of saying that is that this expectation operator is a linear operator. And so when you take the expected value of this product, where one of the terms is a constant, you can instead take the expected value of the random term first and then multiply it by that constant. So we end up with the state transition matrix outside and the expected value of the state plus the expected value of the noise. But the noise is zero mean. That was one of our assumptions. And so the noise term goes away. That's just zero. And we're left with f of n-1 times this expectation. But that's the thing that we started with. That's the estimate of the state at time n-1 given all the measurements up to time n-1. So we end up with a very simple equation then for predicting what the state is going to be at time n. And this is why, I forget which one of you were in this circumstance, but one of you, in thinking about your project, was saying, well, maybe I can see how well the tracking algorithm is doing by leaving out measurements and letting the tracker track over some period of time. But really, in that case, you're just going to be following the process model, feeding state estimates into your process model. You can't take account of a measurement because you don't have one, and then you advance it forward again with your process model. And that's not really taking advantage of the Bayesian framework, because you're just using your prior knowledge at that point. You're not using any of your measurements. You're not looking at how well the Bayesian algorithms are able to combine the prior knowledge and your measurements to create a good estimate. I mean, it works for a period of time, but that's really not an indication of how well the tracking algorithm works. That's how well it works when you don't have measurements. So anyways, this is often called the time update. And at the end of the day, it ends up being obvious, but that's basically how that result is arrived at. Any questions on that step? No? Clear? Great. This gets harder. Okay, so this time update for the state error covariance. So we now know how to calculate the predicted estimate of the state, but how do we go from the filtered state error covariance at time n-1 to the predicted state error covariance? So something else we need to do. Well, if we look at how it's defined, it's the norm or the expected outer product of the error. And we know the state is related to the previous state by the process model. And we now know that our predicted state is also related to the process model. There's no noise term, but it's just the state transition matrix times the filtered estimate of the state. And I'm going to define this other term, the state error vector, with a tilde. So when there's a tilde on top, that means the difference between the true and our estimate. And we can express this if we substitute in the expression for x of n from our process model, and substitute in the result we just arrived at for our predicted estimate of the state vector, we end up with these equations. And both of these terms are multiplied by the state transition matrix. So you can reorder the terms a little bit, and we end up with this difference. And if you look at that difference carefully, you'll see that's also the state error, but it's the state error not at time n given n minus 1, but rather the state error at time n minus 1 given n minus 1. So this is the filtered state error is the difference there. So we can express the state error vector more compactly this way, and that enables us to write an expression for a state error covariance matrix that simplifies the math a little bit. So the state error covariance matrix, the thing we're trying to get to is, again, the expected outer product of the state error vector, the predicted state error vector, and now we've got a more compact representation of what that is. I can't go backward on the slide, so I'm pausing as I go through all these equations. I know some of you are probably tired. I'm not expecting you to follow all this math, but I hope there's enough on the slide that you can always come back and review it, and it will be clear after you've had some time to digest it.
So in the last line, the x tilde is n minus 1 and n minus 1. Can you write that in a similar form as the definition line? So does that?
Yeah.
So it's a state at n minus 1 minus the estimate at n minus 1 given n minus 1? Is that what that means? Or
That is that same thing. It's not a very good arrow, but yeah, you understand what I'm trying to show. So it kind of is there implicitly, even though I didn't write it out explicitly. Yeah, all right. I'm getting lots of head nods. I'm going to continue. Okay, so our predicted state error covariance matrix, these are the same two lines that we had on the previous slide here. We just got our more compact representation that we had. And now I've got to expand this out. You know, I'm using this, this norm notation to really denote the expected value of an outer product, but now I'm going to write that out as the expected value of the outer product. And then you multiply out all the cross terms and take the expected value of all those terms individually, and we end up with 4 different terms as you would expect. I mean, it's basically a kind of like a quadratic. And if you look at this carefully, here we've got the expected value of a constant times an outer product times another constant that is known. And so you can pull those constants outside of the expectation operator, again, because it's linear. And so we end up with f of n minus 1 times the expected value of that outer product. These two terms are the cross terms. And the nice thing about the cross terms is that they're 0, because this noise is uncorrelated and only affects what the state is at time n. It is uncorrelated with the entire history of all the previous measurements and all the previous noise terms. That's part of the reason we needed to make that assumption of uncorrelated noise. So this cross term is 0, this cross term is 0. And the fourth and final term of that product is just the measurement noise covariance, which we assume is known. It's part of our process model. So that's just q of n minus 1. And this other term, the expected value of this outer product, if you look at it carefully, this is the filtered state error vector that we're looking at. And the expected value of the outer product of that vector with itself is the filtered state error covariance matrix at time n minus 1. So we're there. We've got, we arrived at an expression for our predicted state error covariance matrix in terms of things that are known, our process model parameters and the predicted state error covariance matrix that is known from the previous time step. Okay?
So I know you can't go back, but on the previous slide you had, or the error x, the tilde, is defined as the true state minus the estimated. You don't ever have the true state.
And
Or
at
is
the-
that,
You're right, we don't. But at the end of the day, this is defined in terms of an expectation. And when we go through and we do all the math, it ends up, we don't need the true state because it turns out we're always ending up working in with the differences between the true state and the estimate. And so all we need is to know ultimately what the state error covariance is, because this is really an expression of how that state error covariance changes due to the process model.
and we start with an assumption of the error covariance
Yeah, P0,
at
0.
times
Well,
zero.
you start off with your initial state covariance. At time zero, the way you seed the thing, what you start off with is saying, this is what I think the mean is, and this is how much uncertainty I have. So you start off with that. So you're starting off with basically this I guess that would be n equals 1, because it would be n minus 1, which is 0. So it's p of 0 given 0 is something you specify. That's how you started off. And now from 0 given 0, you can now calculate 1 given 0. And I'll show you in a minute how to go from 1, 0 to 1, 1. And as you would expect, if the process noise is very high, then it's going to make this bigger, right? If you've got a random walk model, this is the identity matrix. The state is equal to what it was plus some noise. And so whatever your noise was at this point in time, depending on how much your measurements helped, but you start off with this, and then you're predicting one step into the future. And the growth in uncertainty, the growth in your error is driven by your process noise, which is what you would expect. The more process noise you have, the more your prediction, the more uncertainty you're going to have about predicting your state one step ahead into the future. Any other questions? Okay, there's really just 4 steps. So that was the second step. We need 4 things. We need to know how to predict the state, how to get the predicted state error covariance, which we just did. We also need to know how to get the filtered state estimate and the filtered state error covariance. So there's 2 more steps remaining. Okay, the so-called measurement update. This, in some respects, is the hardest part. This is the slide where I have to apologize, because you can show that the Kalman filter really is optimal without having to make any kind of assumptions, but it takes a lot, and it's more than I can do. So I'm going to disclose the hand waving in this slide, but there's a little bit of hand waving. So suppose we know this. We know what our state is, an estimate of our state at time n, given all the measurements up to time n minus 1. And now we want to make use of that measurement, and we want to do it in an optimal way to get our filtered estimate of the state. And ultimately, I just want to bear in mind, because this is easy to get lost in studying the recursions, and it's easy to not appreciate this, but really, this is not the Kalman filter gain. This is just a different gain. I probably should have used a different variable there. But ultimately, what we're really trying to do with the Kalman filter is take a linear combination of every single measurement we ever get and use that to get an estimate of the state in a way that also accounts for the process model. But this can be expressed as being a linear combination of all those measurements where the process model goes into calculating that gain. And what isn't shown in the book we're working with, but can be shown, is that it turns out that the optimal estimate of the state, when you've got a linear process model, is a linear combination of all your measurements. And the book doesn't show that. It can also be shown that you can do this recursively, that you don't have to go through and recalculate this massive linear combination. Remember, each one of these is a vector. At every time, you get a set of measurements. And so I've got a stack here, not of scalars, but a stack of vectors that's growing in time. So this is an enormous thing that I'm trying to show you here in practice. But it can be shown that you can do this recursively when you've got this Markov process, when you've got this process model. That's part of the reason these state space methods are so powerful. And our book doesn't prove any of that. It just expects that you're going to accept it. And I'm going to do the same rather than spending an entire class just on the Kalman filter going through all that. So, so I can give you a great reference if you want to see those proofs and you want to see more rigor in the derivation. But I'm going to ask for your forgiveness on this one step, and let me assume that in going from your predicted estimate to your filtered estimate, that really all we have to do is figure out what the Kalman gain is on the difference between our measurements and our predicted estimate of those measurements.
So the optimal estimate, is that the marginal posterior or the joint posterior? Because you're going
Well,
recursive.
Yeah, it's a great question. In the Gaussian world, they end up being the same. And there's an argument that unless you've got really weird noise, like I was talking about before, because you're taking linear combinations of things, that the central limit theorem makes things Gaussian. That's why if I keep saying if it's unimodal, I say if it's unimodal, that's good enough. And I haven't worried a whole lot about what the shape of that mode is, whether it's got heavy tails or whether it's a very short-tailed distribution, more so than the Gaussian. And the reason for that is the central limit theorem has an effect here because you're taking linear combinations of random variables. And we've got uncorrelated noise, and in that case, anything that's unimodal becomes more and more Gaussian-like, usually, with time because of the central limit theorem. So, so again, we've got our predicted estimate, we've got our predicted state covariance matrix. We know our measurement model, that's given. We know what the measurement matrix is, and we know what what the covariance is of our measurement noise. I'm defining a new variable here. This triangle term means that it's not only an equality, but I'm also making a definition. So this variable that I've denoted en, this random variable en, is called the innovation. And this is also underappreciated with the Kalman filter and all the generalizations of the Kalman filter, including the incented Kalman filter and the extended Kalman filter. These innovations are really key. The innovation is defined as the difference between your actual measurement and the predicted measurement. And the predicted measurement is based on, it's defined here. It's the expected value of y of n given all your measurements up to time n minus 1. And we know, well, y of n, given our measurement model, is equal to that. And so we're just taking the expected value of these two terms. The expected value of that noise is 0 because that's part of the knowledge we have. It's 0 mean. And the expected value of a constant times x of n is just going to be that same constant, our measurement matrix, times our predicted estimate. So the way you calculate the predicted measurement is you take your predicted state, multiply it by your measurement matrix, and you've got it, and that's it. The innovation is the difference between the true measurement and your predicted measurement. And if things are going well, then that innovation process is white. And this is the single most useful tool you have for tuning the Kalman filter to your data. When you feed it actual measurement data and you look at these differences, they're usually not going to be white because your model isn't accurate is part of the reason, but also it's because usually your model's not accurate because you haven't tuned it yet. You've often got parameters, and it's usually your process noise covariance that you can adjust to make your model fit the data. So in Golriz's example, she's got a lot of parameters in that process noise vector, and she's got no idea what they are. I mean, no one gave her the process model. Well, I mean, you kind of had it from the paper, but the people who wrote the paper had to make that up somehow. And how on earth do they come up with that? I mean, it's kind of a made-up model for a cardiovascular signal. And how on earth do you think about what's reasonable there? Well, one way to get an idea of what's reasonable is to look at differences. And you can look at spectrograms of those differences as well and get a lot of information. Because I said it should be white, but in general it won't. And we've got a harmonic structure. You can see which harmonics are still present and which ones are not. If there's harmonics that are present, then you know you're not tracking them very well when you look at this difference. So that can give you a lot of information. And those of you that took the class last spring with me where we talked about characterizing processes, estimating power spectral density and autocorrelation, all those tools are very helpful for tuning these state space models. by studying the innovations and looking at how white the innovations are. When they're not white, it gives you a lot of clues, especially if you've got more than one measurement and you've got a good engineering intuition about how those are related to your state vector, if you really understand your measurement model. So if you understand, I'm tracking a kayak, I'm tracking a truck, I'm tracking a roast, whatever it is that you're tracking, that you've usually got knowledge that if you've got differences there, you can use engineering domain knowledge to help guide you as to what's going wrong in your process model that is causing those innovations to not be white. So it's very powerful, and that's the reason I call them out kind of separately, unlike what the book does, where I think it just substitutes in that difference. It says Kn times Yn minus this without even ever emphasizing that this is a prediction of what those measurements are, and that if that prediction is going well, if the Kalman filter is doing its job well, if you've really got an appropriate and accurate state space model, then these innovations will be white. Extremely useful tool. But anyways, that's not really our purpose here. That's mostly an aside. Our purpose here is that the way that the filtered estimate is calculated from the predicted estimate is that basically there's a Kalman gain that is multiplied by the innovations, by that error, and that's used to update your filtered estimate. Golriz?
So why I missed it? Why there is a harmonic in the error? Why there is an error in the process model? Or
Okay, so I know a little bit about what you did your homework presentation on, about that particular model. And you've got a stack of harmonics. You've got a quasi-periodic signal that is basically being represented by a Fourier series with a fundamental frequency that is fluctuating over time. And so every one of those harmonics has an amplitude. And if you know your process model, if you say the coefficient of the fifth harmonic, the amplitude of the fifth harmonic, I think is not changing very rapidly. And so you give it a very small process noise standard deviation. You say, my prior knowledge is it's not changing very much. But then you apply it to a signal, a real cardiovascular signal, and you look at the difference between your signal and your predicted estimate of that signal that's coming from your Kalman filter. You look at that difference and you look at it with a spectral analysis, and if you look at that difference, there shouldn't be anything there. It should be white noise. It should be flat. But you look at it and you see, oh, I've actually got power at the frequency of the third harmonic. Then that tells you you're not tracking very well. And if you're not tracking very well, it's usually because you haven't, your prior knowledge is wrong. In that case, you haven't given the model enough flexibility. It's not able to adapt that coefficient rapidly enough to keep up and make these innovations wide. You're basically telling it, keeping that coefficient, your prior knowledge is that coefficient is changing more slowly than it actually is, and so you'd end up with a problem there. And you could see that in a spectrogram. There were some bugs, I think, in what you presented. So I mean, it's not, you looked at the spectrogram and it's just horizontal lines, but it shouldn't look that way. And if you looked at the innovations, which you'd do like if you're doing that for your final project, then you could tell how well you were tracking. It was actually a key tool when we further developed that model, where we saw, oh, we're missing some things. We realized that there was a frequency modulation effect also that we published in a later paper and in one of my students' dissertations, where there's a frequency modulation effect that we saw by looking at a spectral analysis, a spectrogram of these innovations, and we saw there are these side lobes that we're not capturing, and it was explained by frequency modulation effects. So it was very helpful to us. Any other questions so far? Okay, so I'm asking you, I'm sorry, but I'm asking your sort of forgiveness here that we're assuming, I say, how do we get from here to here? And I'm giving you the answer without proving it. This is one bit of hand waving I'm doing, that I'm telling you this is optimal without showing it, that it really can be expressed recursively and is some gain that we'll solve for times the innovation. But that can be done rigorously. It's not done in our book, but you can find that elsewhere, including Kalman's paper. So there's a lot of different ways you can define the error. We're trying to track the state optimally, and one problem with that is you could say, well, isn't there a trade-off in estimating one part of the state compared to another part of the state? What if I say, I want to estimate heart rate and respiratory rate optimally, but it seems like there would intrinsically be a trade-off between those two, that maybe you could estimate one more accurately at the expense of estimating the other one less accurately. And it turns out that's not true for the Kalman filter. The way it's framed, you can, I'm expressing it this way, but even if you weighted different elements of the state error vector, and you said, I care much more about this element than the other, it turns out the Kalman filter still gives you the optimal estimate of the state. There's not that trade-off that you might have expected, and that makes the result all the more compelling and valuable to us as engineers. It's part of the reason the algorithm has withstood the test of time. So one way of expressing this is if we take our state error covariance matrix, the trace of that is just the sum of the different elements. This is unweighted, but nonetheless, this is one way of expressing it. Is the trace of the filtered state error covariance matrix. So we could say that's what we want to minimize. We want to figure out what estimate of the what filtered estimate will minimize the state error covariance. So if we accept that as our error criterion, then we've got to minimize that. But before we can do that, we have to do the fourth step, which is figure out what our filtered error covariance matrix is, because I haven't given that to you yet. So we're going to skip ahead to step 4, and then we'll come back and finish up step 3. Step 4 is getting a recursive expression for that. And that's more of this same type of math. It's defined as the covariance of the filtered state error covariance, which is defined as just that difference. And we now know that the filtered state can be expressed as the predicted state with the common gain times the innovation, which is that difference. Excuse me. And if we take this difference is actually can be written as our state error with that tilde notation. And if we look at the terms, what do I do? If we substitute in for our measurement model, how it's related to the state vector and the measurement error, I substituted those in for y of n. And then we can collect common terms. We've got kn times hn times xn, but then minus hn times x of n given n minus 1. And so those two terms can be combined as kn times hn times the predicted state error minus the common gain times the measurement noise. Both of these terms are being multiplied by the state error, so we can collect those and write that as the identity matrix minus the product of those two matrices times that error. And then we've got a difference of just two terms that we're taking norm of. So then you can multiply that all out, and again we end up with the cross terms, and this term times this transpose, and this term times this transpose, and then the two cross terms. So we end up with the 4 different terms, just like when you multiply out a quadratic. And as before, we assumed that our measurement noise was white, and so it is uncorrelated to all the previous measurements that are accounted for in this measurement. So the two cross terms go to 0 because the measurement noise is white. That's where we're taking advantage of that assumption. And so we're left with just these two terms. And those two terms, as before, we've got kind of this matrix that's known times an outer product of 2 random vectors. So the expectation operator is linear. We can bring that inside and we end up with this norm. And same thing for the measurement noise. It gets kind of sandwiched in between these two matrices, and so we end up with this expression. And if I pull that ahead to the next slide, the two norms that are listed there, this is just the predicted state error, and so that's the predicted state error covariance matrix. It's a mouthful. And this is the measurement noise covariance matrix. And so once again we end up with a result that's really nice. We've got the fourth step that we needed. We've got the filtered state error covariance matrix can be now expressed in terms of the predicted state error covariance matrix, common gain, measurement matrix, and the measurement error covariance. Cool, huh? Yeah? Any questions? guys, you're killing me with all this math, but I wanted to show it to you. I wanted you to see where the Kalman filter recursions come from and not just say, here they are. I wanted to go through it with you. So, all right. So going back, well, lucky you, we're out of time. So I guess we'll come back to that third step on Tuesday, and I'll finish this up and show you some examples and give you some more tips about how to tune with the Kalman filter. So we'll finish this up on Tuesday.